In this video, I will introduce you to PU learning methods that work by incorporating your knowledge about the labeling mechanism. These approaches are very interesting because in theory, some of them should be able to train the correct classifier. So I will show you why we can expect this in theory and also what still would be the practical challenges towards actually learning these. I hope it will be very insightful. So we are going to learn from positive and unlabeled data by incorporating the labeling mechanism. So naturally, the first question to ask is which labeling mechanisms can we actually incorporate? Well, most of these PU learning methods were developed for the SCAR assumption. Under this assumption, every positive example has the same constant probability to be labeled, which is the label frequency. So the propensity score for each instance is equal to the label frequency and it hence does not depend on the features. Remember that knowing the label frequency is actually equivalent to knowing the class prior. Therefore, knowing the class prior is enough for applying these methods. One method can be generalized to the SAR assumption. So this means that any propensity scores can be incorporated. I'll mention it when we get to this method. To demonstrate the methods of this video, I will be using this very simple example. So here we have a data distribution that only consists of one feature, which is the x-axis here. And we have a negative distribution and a positive distribution. So the negative examples will be mostly here, but also a bit on the outliers. And the positive examples will be mostly here and a bit on the outliers. From these two distributions, we can then see that the probability goes up like this. Now let's consider the PU setting for these distributions, where only a fraction of 0.3 is labeled of the positive examples. So the labeling frequency is 3. Now you can see this is the distribution of the labeled examples, and it looks the same as the positive examples, but it's scaled down. This now will be the distribution of the unlabeled example, which is the sum of all of the positive examples that were not labeled and the negative examples. The probability for an example to be labeled is going to be 1/3 always of the probability of that example to be positive. So you see here it only goes up to 0.3. But it's otherwise also the same shape as the probability for an example to be positive. It is just scaled down. There are three main classes of methods on how to incorporate the label frequency for PU learning. First, there is a post-processing method, which trains a non-traditional classifier that can predict the probability for an example to be labeled, and then later adjust this non-traditional classifier using the labeling frequency C. Second, there is a pre-processing method where we first re-weight the data and then train a classifier from the weighted data. For the way to re-weight the data, we use the labeling frequency C. Lastly, there is the modification method, where we actually change the learning algorithm for a certain classifier to incorporate the labeling frequency C. Let's start with the post-processing methods. Here, we first learn a model to predict the probability for an example to be labeled. Of course, these methods are going to work best when we have a perfect model for this. So let's first look at the scenario where we actually know the exact probabilities for each example to be labeled, which is of course equal to the labeling frequency times the probability for each example to be positive. From this, it follows directly that the first thing that we could do is to just scale the distribution. So we scale the probability distribution for examples to be labeled with 1 over the labeling frequency. And then we get our probabilities that they are positive, like again. So here we would have the probabilities for examples to be positive and the probabilities for examples to be labeled. And we can just scale this one back up by using 1 over C. That's it. But maybe we're not interested in knowing the entire distribution. but we are just interested at knowing which examples would be classified as positive and which ones would be classified as negative. So this we could see by looking at the probability line of 0.5. So you can see that all of the examples above this line, so basically all examples to the right, would be labeled as positive, and all of the examples to the left would be labeled as negative. So a second method for post-processing would be to look for the probability threshold that works with the probability distribution for examples to be labeled. So here too, we would like to have the examples on the right to be labeled as positive and on the left to be labeled as negative. So this means that the new probability threshold should cross the probability distributions for examples to be labeled at the same place in the feature space as the old probability threshold crossed the probability distribution for examples to be positive. Now, because all of the probabilities for examples to be labeled are just a scaled down version of the examples to be positive, this new probability threshold will also just be the old one, so 0.5, scaled with the labeling frequency. So in this case, it would be 0.15. The question now is, can we actually learn a good non-traditional classifier to find the probabilities for an example to be labeled? For sake of comparison, let's look first at how good we are at finding a traditional classifier to predict the positive probabilities. Here in orange, we have the real probabilities for examples being positive. To the data that we generated from our positive and negative distribution, we applied three classifier learners. There's a decision tree learner, which you can see from the staircase. And then there's a naive Bayes classifier using Gaussians and a logistic regression classifier. So you can see that all of these three classifiers do pretty well at finding these probabilities. Now let's look at the results for the positive and unlabeled data. This was clearly a harder task. So again, we have the probabilities, the actual probabilities, and then the classifiers did their best to find those. So you can see still the decision tree learner. Actually, this one does pretty well. Like it does not much worse than it did at the fully labeled data. Then we have the logistic regression one. So the logistic regression, it always learns a sigmoid function. And this one was actually very hard to map because there is no space where the probability for an example to be labeled actually becomes ones. And this is a bias of the logistic regression that it's very difficult to map to this data. Lastly, we have the naive Bayes classifier, and what it does, it's a naive Bayes based on Gaussians, is it tries to map the positive and the negative distribution both to a Gaussian and then use those to get a probability of it being positive or negative. This worked pretty well for the supervised case with all the data because the positive and the negative class actually were Gaussians there. But now our labeled class is still coming from a Gaussian distribution, but the unlabeled ones, it looked more like this. So it's a mixture of Gaussian, which the naive Bayes classifier will model something like this. So that's why the probability for an example being positive, being labeled, goes down again here at the end of the Bayesian classifier. So we see again that we have problems with the classifier bias in this case. So many of the classification algorithms that work for supervised data get into trouble with unlabeled and labeled data because the entire space of labeled data will now also be covered by the unlabeled class. And that's typically something that's very hard to deal with for binary classifiers. They can deal with some overlapping space, but when the entire positive space overlaps with the negative space, then it becomes quite hard. You see, actually the decision tree is the only one that could handle this well in this case. So I do not want to draw conclusions on which classifier is best or not, because this is going to be very application dependent, but just to show you that it's not because a certain classifier works well when we have all of the data available, that this will still be a good classifier for the non-traditional classifier. So let's look at what happens with our post-processing methods if we use those bias probabilities for examples to be labeled. So here we have our probabilities for examples being positive. Here are the real probabilities for examples being labeled. And then this yellow full line are the probabilities predicted by the logistic regression classifier for examples being labeled. If we scale these up with 1 over the label frequency, we get our predicted probabilities for examples being positive. Now you can see that actually these probabilities go up way too high. They go over 1, which is of course not possible for probabilities. So this is quite problematic, and the simple thing that we do here to deal with it is just say that whenever it's larger than 1, just make it equal to 1. So you see any mistake that's made by estimating this classifier for the probabilities to be labeled will be of course translated into the final estimator. Also, if we are just going to look at the probability threshold, of course this is just 1 point instead of all of the probabilities. This can also still be wrong. So here we see that actually we are going to label less examples to be positive. Because of the overlapping positive and negative classes that this non-traditional classifier is trained on, it's actually quite common that the threshold would be in favor of the negative class. So more examples would be predicted as negative than the optimal model would do. So we can see that a problem for these post-processing methods is that many classifier training algorithms actually do not have the correct bias for learning from PU data. And specifically, these overlapping labeled and unlabeled spaces are very tough to learn from. So we'll often get a negative bias. And therefore, we might prefer looking at other options. So maybe if we just weight the data so that the labeled examples get a higher weight than the negative ones, this problem will be solved. So this is what we're going to look at in the pre-processing methods. The first idea for reweighting the data is to pick class-dependent weights. So all of the labeled examples will get a same weight W plus, and all of the unlabeled examples will get the same weight W minus. Of course, because we want the labeled examples to have a bigger influence on the learning, we will have a bigger weight on the labeled examples than on the unlabeled examples. So similar to training a non-traditional classifier, we will be using the unlabeled examples as negative examples and the labeled examples as positive examples. But now the difference is how we are going to weight these examples. So how do we choose the weights? Well, by class weighting the data, we can make sure that a certain probability in the non-weighted data corresponds to a new probability in the weighted data. An interesting probability in the non-traditional classifier was 0.5 times the label frequency, because this we would take as a threshold probability. And this threshold probability in the weighted, in the model after weighting the data, we would like it to be 0.5. So the weighting scheme would be for the positive examples to have a weight of the probability that we would like it to be divided probability that it used to be, and for the negative examples it would be 1 minus the probability that it used to be over 1 minus the probability that we would like it to be. So with our chosen probabilities, this would be 0.5 over 0.5 times the label frequency, which then of course equals to 1 over the label frequency. And for the negative examples, this would be 1 minus 0.5 so this is just 0.5 also, over 1 minus 0.5 times the label frequency. So this equals to 1 over 2 minus the label frequency. And these are going to be our final weights. In the ideal scenario, our model will be able to capture those scaled data distributions. So let's look at this case. Again, we have the negative data and the positive data, and we have the labeled data here and the unlabeled data there. So now what we did was scale up the labeled data with 1 over C. So this actually gives you the same distribution that we had again for the positive data. And then our unlabeled example, we will scale it down with 1 over 2 minus C. So the resulting probability distribution that we get is this one here. So you see that indeed it has the correct decision probability. So we will actually label the same examples as negative as the real probability distribution did, and the same examples as positive as well. But the probability distribution that comes from the scaled, labeled, and unlabeled data does not look the same as the probability distribution that comes from the actually negative and positive distributions. Particularly, you can notice that the probabilities for positive examples are way too negative, so are way too low, so they're negatively biased. The reason why that is because even though our labeled distribution now looks the same as our positive distribution, our unlabeled distribution here is way larger than the negative distribution that we had there. So this part, it has quite a big probability mass. It will make sure that the positive probabilities are too low. We can make the same observation when we actually learn a real classifier from real data. So this orange line is the actual probabilities that we want, and the other orange line, the thinner one, are the probabilities that we expect from this reweighting. So we can see that in blue our different classifiers indeed follow the thin orange line, so they're also giving too low probabilities for the positive examples. So with this method, we get a negative bias. Additionally, we still have the same problems that we also had with the post-processing method, that it might be hard to train a good classifier from this kind of data due to the classifier bias. So for example, our logistic regression here still needs to make a sigmoid that goes up to 1, which is not ideal for this case. And our Gaussian naive Bayes function, it still expects both the positive and the negative examples to come from Gaussian functions, but still is not the case here. So again, we have this weird shape. Let's see if there are other ways of weighting the data that can handle these biases better. This brings us to the second idea for pre-processing. So differently from what we had before, we are no longer going to count all labeled examples as positive and all unlabeled examples as negative. We are going to still count the labeled examples as positive, but the unlabeled examples we're going to partially count it as negative and partially as positive. And how much it will count for each class will depend on the label probability of that example, which we can find by training a non-traditional classifier again. The positive fraction of an unlabeled example will be equal to the probability of this example being positive, given its features, but also given the fact that it actually was unlabeled now. The fraction for it counting as negative will be the probability that this is a negative example, again, given the features and the fact that it's unlabeled, which is just 1 minus the positive fraction. These probabilities can be calculated using the label frequency and the probabilities that these examples would be labeled. which we thus get from the non-traditional classifier. So to summarize, we will construct a new dataset which contains all of the labeled examples as positive with a weight 1, and then all of the unlabeled examples also as positive with a weight W plus, which can be calculated from the previously seen formula. And then again, all of the unlabeled examples, so they're added twice, but this time as negative, and they will have a weight 1 minus this probability. In the ideal scenario, we know the probabilities for examples to be labeled, and we also would know the distributions for labeled examples and unlabeled examples. By partially assigning the unlabeled distribution to the labeled one with the formula that we saw before, we actually would be able to recover completely the positive and negative distributions, hence enabling us to learn the correct probabilities. The only problem is that in reality, we usually don't have these real probabilities, but they're biased because we learned them from the data. And as we saw before, this is not always that easy. So how good our actual model will be in the end will depend on how good our estimate of these probabilities for examples to be labeled are, and also how good the classifier's bias now works potentially in our advantage. So it's still not ideal that we depend on the non-traditional classifiers, as we saw that these are not always that easy to train. This brings us to the third idea, where instead of duplicating the unlabeled examples in our new dataset, we are going to duplicate the labeled examples. This at first may sound counterintuitive, but bear with me. So we assume that positive examples get selected to be labeled with a probability C. Let's say that this probability is 0.25 or 1 out of 4. So we would get maybe this one not, 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 this one, this one not, this one, this one, this one not, this one, this one not this, not this, not this, this not this, not this, not this, and finally this one. So now you can see that for every labeled examples that we observe, that we actually expect there to be 4 positive ones, which is 1 over C. So from this observation, we can say, okay, every labeled example has to count as positive with a weight 1 over C. But this is not all. Not only does each labeled example count for 4 positive examples, but it also means that actually 3 of the unlabeled examples should definitely not count as negative. So if we would just take the unlabeled examples as negative, then we actually have too many negative examples because those unlabeled examples should not be taken as negative. So for each labeled examples, we added more positive ones, but we should also for each labeled examples make sure that these that we added are removed from the negative data. So the way that we will do this is add the labeled examples also as negative, but now the weight will be 1 minus 1 over C. So here that means minus 3, because we are essentially removing this labeled examples 3 times from the negative set. So what we did was taking the labeled distribution and scale it up to the actual positive distribution by multiplying it with 1 over the label frequency. The next step was to take the difference between these two distributions, the scaled and the unscaled label distribution, and subtract it from the unlabeled distribution. And this difference actually becomes the real negative distribution again. Because we can reconstruct the actual negative and positive distribution, we should also be able to find the real probabilities. We can see that this is indeed the case. All of our classifiers now fit really well to the real distribution. Maybe I should make one side note on why this is working so well. Well, first of all, this is a very easy learning scenario with two Gaussian classes, but also there were 10,000 data points sampled from those distributions, of which 5,000 were positive. And then with a label frequency of 0.3, we had over 1,000 labeled points. So we were actually easily able to capture this Gaussian distribution from the 1,000 labeled points. In a real scenario, this is of course not always the case that we actually can perfectly capture the labeled distribution. But all of the examples of this video have the same advantages of it being quite an easy problem and having enough labels available. So it is a fair comparison. This weighting scheme can actually be generalized to work with any labeling mechanism using the propensity scores. And it's simply by replacing the label frequency that we used before for each example to the individual propensity score of that example. So the positive weight of a labeled example with feature X will be 1 over the propensity scores of that example. And the negative weight of that labeled example will be 1 minus 1 over the propensity score. So it's as simple as that. On first sight, there seems to be no downside to this weighting scheme. In fact, it has been shown that using this weighting scheme, you are expected to train an unbiased classifier compared to the one that you would train from fully labeled data. But there is one possible issue, and this is that you're training your model with data that has negative weights. And this is not something that every machine learning algorithm can handle. Take a decision tree learner, for example. When learning a decision tree, you are recursively splitting your dataset based on some features that you split on. Then you decide if this was a good split based on the number of positive and negative examples in the newly induced subsets of the data. But because of the negative examples with negative weights that come from the labeled examples, actually the number of negative examples in a subset could be negative, which is really problematic because this is not really possible and most of the splitting criteria cannot handle these negative numbers. Similarly, in naive Bayes, you would estimate the probability for the positive class given a certain feature. So here as well, you are looking at subsets of the data where you again also could have a negative number of negative examples, making it impossible to calculate correct probabilities. We could solve this problem by modifying the learning algorithm to handle these edge cases. And this is exactly what method modification techniques will do. So now we've seen the post-processing methods, the pre-processing methods, and finally we get to the method modification. So most of the method modification methods that have been proposed in the literature are actually based on the last weighting scheme. So the problems that I just showed that we have with the decision tree learners and the naive Bayes were already addressed in the literature to handle the edge cases. For this entire video, I have just assumed that we know the labeling frequency. But you might wonder, why would we know this? Where would we know this from? Or actually the same question, how would we know the class prior? Because from the class prior, we can, of course, calculate the labeling frequency. Well, there are basically three ways to know this. First, you could know this from expert knowledge. So somebody might be able to tell you what the expected class prior is for this problem. Secondly, you might actually have some labeled data available that might not be enough to train an entire classifier on, but it might be enough to estimate the class prior from, and then you can use it. Or last but not least, there exist actually quite some methods to estimate the class prior from positive and unlabeled data. This is a whole field on its own. It comes with other assumptions for enabling you to estimate the class prior and then a bunch of methods to do this. So this is outside of the scope of this video, but this is possible. So if you are interested in it, you can find all the information you need in our survey paper. This was the last video of this tutorial. I have covered on a high level most of the topics that we cover in our survey paper, but not everything. I already mentioned the field of estimating the labeling frequency directly from the positive and unlabeled data. Another interesting topic that I've only brushed over is learning under the SAR assumption, so with a biased labeling mechanism, which might very often be the case in practice. Anyways, I hope it was insightful and that you have obtained a good basic understanding of the PU learning problem so that you can now start tackling your own real-world PU datasets. Bye!